Hello and a very warm welcome on behalf of NTI Audio. When we talk about sound level measurements, there are dozens and hundreds of different terms, parameters, levels that have to be obeyed, requirements from different standards, and so on and so forth. We frequently get questions from our customers regarding what levels are relevant, what has to be applied, in which situation, how to understand these different parameters. So we want to try in this presentation to clarify a number of these most frequently asked questions. Well, my name is Markus Becker, and today Berno Nitsch is assisting me in this presentation. He is the one who will respond to the incoming questions, and if there should be any technical issue, he will hopefully help me as well. The contents that we have prepared for you start with a brief introduction on the scope and the goals of different sound level measurements. We will follow up with a theoretical section which covers the sound levels and the different weightings. We will say something about the measurement execution itself before we present to you a practical part in this webinar. We have also afterwards summarized a couple of typical applications to explain the typical proceedings, how to find the relevant parameters, and we will end the presentation with a short look on the data analysis and reporting tools that we are providing. Last but not least, I will come back to the questions that have popped in and comment some of the answers. This will take approximately half an hour. On these two pictures, you see two typical fields of applications for sound level measurements. On the left-hand side, we have the environmental sector, the neighborhood noise, traffic noise, whatever falls under this aspect of environmental noise measurements. On the right-hand side, we can summarize live events or also occupational noise measurements in a separate segment. How can we differentiate between these two applications? First of all, when we talk about environmental noise, we talk about noise control. So we want to record the sound level over a specific time. Maybe we are interested in analyzing the spectrum, the real-time analysis of that incoming sound. Maybe we have to apply different weightings for the day and for the night in order to identify the annoyance of the sound for the affected persons. So generally we are talking about noise emissions, which means we have no or only little impact on the sound sources, but we can determine the effect of them on the person who is exposed to this noise. On the other side, talking about live events or occupational noise, we are clearly talking about ear protection. We want to prevent any physical damage to the persons who are exposed to that noise, to that sound. So again, we have to measure the sound level over time, but here we have to have a look as well on the maximum or the peak level that occur during the recording time. So in contrast to the first example, here we have a better influence on the sound level. For instance, if you are a front of house technician, you can directly intervene if the sound level is too high. You can put it down, you can reduce it, or you can possibly, when we talk about occupational noise, apply sound protecting or damping materials on the machinery that is emitting this noise. So here we are rather talking about the emissions of a certain event or item to the neighborhood or to the audience. Well, regardless what application we are talking about, we will encounter most assuredly the same level measurements all over. And I'm starting here with two live sound levels, LAF, LAS. Live sound is a little bit a simplification, but it indicates that these levels allow us to get a feedback to read the current level that is present in the place where we are standing, where we have our test instrument located. On the other hand, the more relevant term in long-term surveillance, in long-term monitoring, is the LEQ. EQ stands for the equivalent sound level. And that is a sound level that is averaged over time, over the recording period. And we can apply different weightings, same as for the live sound level. And I will explain more about these weightings just on the following slides. Well, in most cases, we also want to record, to monitor the history of the sound. We want to take a look what has happened during our recording period. And the LAF or the LAS are less suited for different reasons. And for that reason, in most cases, we are using the short-term LEQ, which means that we are averaging the LEQ in small slices, for instance, every second, every 5 seconds, depends on the application. You see down here in this graph, the blue curve is the LAQ DT, so the short-term LAQ, which gives us an information about the sound level at the corresponding time, and we have the averaged LAQ over the whole recording period. What is important to keep in mind that these three levels are RMS, root mean square levels, and that refers to the calculation method to get to these levels. It is important because there is a fourth one, the peak level, the peak sound level. That is calculated in a different way. It is not an RMS calculation behind that. And that is also the reason why the peak level will always be higher than the LAF, the LAS, whatever you look at. Now, there's even another possible cause of misunderstanding, and that is the difference between the maximum and the peak level. On the first sight, you could think this is the same, but it is not. So let me explain that with this graph. Here we have plotted the blue curve is the LAF over time. Well, the highest LAF value up to the corresponding time would give me the LAF max, which means if I look at this graph now, so we had here in the past apparently a higher level, and that was superseded by this peak, the next one. Every time that the LAF reaches a new highest level, the LAF max result will follow and stay there until we have an even higher level. So you can see that the LAF max is the highest LAF that has occurred during our period of observance, during the time when we have been recording our measurement. And now you understand that we can do the same for the LC peak. We can take a look where was the peak at its highest point, and you see here this green curve gives us the corresponding result. So here we have the LC peak max, the maximum level that the LC peak measurements during the recording ever have reached. I have already mentioned these weightings, and there are actually two different weightings. Let me first say something about the frequency weighting, A, C, or Z. These frequency weightings have the intention to emulate the human ear, the way as how we humans perceive a noise. And this A weighting curve is the most popular, the most well-known one, represents our, or in a simplified way, represents our human hearing perception for noises up to 100 dB. So we can see that we are less able to hear a sound in the low frequency range, and our ability declines also for the high frequency sounds, but here our ear is quite good quite good performing around 1000 Hertz, for instance. For higher levels, we would apply the C weighting curve. Apparently, if the sound level is higher, our ear has a better ability to identify low frequency sounds. And last but not least, the set weighting is a little bit misleading because it's not actually a weighting, it's a linear representation of the test instrument, of the result from the test instrument, which means it's actually an unweighted curve. So Z weighting means the technical sound level as it is measured by a precisely working test instrument. Well, in reality, the LEQ and the LCEQ play a major role for sound level surveillance and sound level measurements. The LEQ, for instance, is the essential value for the audience, for instance, in a concert or also in an industrial hall. So for the people who are very close to the sound source, who are exposed to the sound coming from the PA system, coming from a machine. And if we want to determine the maximum allowed level or whether the actual level exceeds this given standard or not, we have to look for the LAEQ because that is the relevant value for the people who are close to the sound source. On the other side, if you imagine a concert hall, and I guess you know that especially low frequency sound has a higher, better propagation than the high frequency, which means that outside this concert hall, you would rather hear the low frequency sound. And for that reason, because the C weighting better reflects or to dampens in a reduced amount this low frequency components, the LCEQ is more relevant for the neighborhood. And that is the reason why a couple of countries have just recently changed their standards for noise monitoring from A weighting, not to C weighting, but both of them. So they say A weighting for the directly affected people and C weighting for the neighborhood. Both measurement values are relevant for the overall situation. Here we have a slide for the time weighting, and the time weighting has a different objective. Here we're talking about the readability of the live level. I have plotted here the technical result from a sound sampling. So the test instrument, as you know, regularly in a very short with a very high speed samples the incoming sound, and that is the result what you would see regardless whether we have speech or music or whatever kind of noise, ambient noise, we will have a rather stochastic pattern. So if you would display every single measurement result on the display on the screen, you would hardly have any chance to read out any significant result because the numbers on your LCD would jump up and down, back and forth. You couldn't see anything. There would just be a huge mess of dancing numbers. You have no chance to find out what is my level right now. And for that reason, we have to somehow dampen these test results in order to make it readable. And this is done by these time weightings, and here the standard basically has two time weightings that are most relevant, the F fast and the S slow. And to explain that, I want to show you here this schematic graph where I have a very silent situation, a low noise at 50 dB, then I have a sudden and very sharp rise up to 80 dB. The sound stays there at this level and it drops again very quickly down to 50 dB again. How would that test instrument with the fast weighting react? And that is shown here in this curve. So the green curve represents the displayed level over time. We have this very sharp rise here, and the display follows with a certain inertia, so it follows a little bit later. It is the attack time here is given by this time constant, which is defined by the standard. So you see that within a little bit less than a second, the instrument will show you the new level with a certain delay towards this initial rise. And the same happens here at the decay, because the standard defines the decay time for the display of the instrument until it reaches again the new level of the actually existing sound. The same applies for the slow weighting. Here we have a higher time constant, which means that it takes a little bit longer for the test instruments to display the new level that has already changed for up here. And the same applies for the decay. When the sound is switched off, it takes longer time for the test instrument to display the new level. So it is just slower. It has a higher inertia compared to the original sound, and that makes the display better readable. Well, when we talk about measurements or recording data, mainly in the first row we talk about wideband level. We want to know the overall level within the audio range from 20 Hz to 20 kHz. However, in some applications we want to see the spectrum. You remember, especially environmental noise. Here we may have to identify some specific components in a noise signal, not just the overall noise, but specific frequency components. And for that purpose, we have different resolutions. We have the octave band resolution, which is rather rough. We have the third octave band resolution, or even here the 12th octave, which is a pretty high resolution display. And you see this display has the most significant feedback for us. For instance, here, this is the same signal for the three displays. It shows me that we have a fundamental frequency and some upper harmonics. Keep in mind, please, this 12 octave display is only available in the XL2 if you have the spectral limits option installed. The other two resolutions are provided by default. And there's even a third way of recording data, and that is to record the audio file in wave format. That allows you to listen to the whole event after it has happened once again. For instance, if you want to identify a specific event during the recording. And we are offering this wave file recording in two qualities. The compressed one, which minimizes the amount of memory that is used on your SD card, or the full linear high resolution wave file recording, which however requires this extended acoustic pack option to be available on the XL2. Well, when we are ready to execute a measurement over a certain amount of time, we also have to consider the way how we record this measurement, how we execute it. And here we have three different ways. The first one is the continuous mode. That means we start the measurement, we record it until we press the stop button. So that's very simple. We press the start button, it starts, we press the stop button, and it ends. The second way is what we call the repeated or repeated synchronized mode. And here we manually start the measurement again, but now it's not a continuous recording, but the measurement is executed in blocks. See that here. So we start with the first block, for instance, 1 hour or half an hour, depends on your settings. And after this time period, the measurement saves all the data and restarts the next period, the next measurement period, and the third and the fourth, and so on. So the measurement duration is divided into slices of a predefined duration. These are these repeated blocks. Synchronized means that these blocks are also synchronized with the real-time clock. For instance, let us assume you would start at 8:10 with your recording, and you have block length of half an hour, which is synchronized. Then the instrument would continue until 8:30, complete the block, start the next one to 9 o'clock, from 9 to 9:30, and so on and so forth. That is the synchronized mode. And the third method would be the gliding, or some people call it sliding or rolling recording. What does that mean? Here again we have to determine a certain duration which we record, and as soon as we are at this point where the first 60 minutes, for instance, have been completed, we continue the measurement by looking always for the past 30 seconds, for the past 60 minutes. So this would look like that. We continuously consider only the past 60 minutes. We are always here at the front time, at the top of this block, and we're looking back for the past 60 minutes. Regardless where we are in this time axis, we always look back for just 60 minutes, and that gives us our current result. Before I start with the practical presentation, let me very briefly summarize the necessary preparations before you start a measurement. Of course, you have to connect the microphone. Maybe you want to verify the sensitivity of the microphone by using a microphone calibrator. You have to adjust the input range, which corresponds to the sensitivity of the sound level meter. We recommend the highest range for live events and rather lower ranges for environmental noise, because there you have most frequently rather silent environments. Then the recording mode, that is what I just showed you on the last slide, continuous or repeated. And of course you have to decide which levels you want to see here on your display and which levels shall be logged. We strongly recommend to save all these settings in a profile and load it before you start the measurement. The main reason is it takes off the burden of adjusting everything correctly just before the measurement starts, so you can do that quietly in your office day before whenever you have time. It's just much less stress. You can even download predefined profiles from our website. We are supplying them for various standards. The details of all these settings, by the way, have been presented in other webinars and previous webinars, so I don't want to spend much more time on this aspect here. I rather want to hop over to the practical presentation, for which I have connected my XL2 via USB to my PC. I'm running the new Projector Pro software to show you the screen content of my test instrument, and I'm using Emma Pro with a loudspeaker in order to create some sound that you will see right now. So let me switch over to that screen content of the XL2, and what you see now here is the sound level of my voice. And maybe you notice that only two results are visible, the LAF and the LAS. The reason is quite simple. Here we have these live levels, as I stated before. The other measurements, the LAQ, the LAS max, and the LC peak, must be started before we see any result. And that is what I'm going to do right now. You see very quickly the test instruments start calculating the average here in the LAQ, and it shows me this maximum LAF and the maximum LC peak that have occurred since I have initiated my measurement. What you also see, by the way, is when I'm talking that this LAS result is much more stable. It's much easier to read out that I'm apparently talking at about 60, 62 dB, while if you look at the LAF, it is jumping much more nervously, so which means it is quicker in its response, but that makes it also a little bit less good readable. And the other aspect I want to point out is here these stable maximum results. Let me clap in my hand for a second and you will see what happens. You see immediately the maximum have jumped up because apparently my clap was much louder than everything that has happened before. It would be hardly possible to read out this value by watching that measurement result all the time, and for that reason this is a very comfortable solution for these maximum detection. And maybe you have noticed that the LAQ did not show mainly or any major change when I was clapping, because the energy in my clap was much too low to have a major impact on this long-term average up here. Now let me swap over to the graphical display, to the spectrum. This is apparently the spectrum of my voice. And I will now connect the Emma Pro. I will activate the Emma Pro with a pink noise signal, because I want to show you the shape of the pink noise with the different weightings. So it takes a little bit of time until everything has settled. Now I'm going to switch on my pink noise generator, and you see that here the definition of pink noise is same level over the whole frequency band on the logarithmic scale as it is here. Well, when I change the resolution first from octave to third octave, you see I have a clearer picture. It's almost the same as before, but you see I have a higher resolution. And now what I'm doing now is I change from the unweighted Z weighting to A weighting. And then you will immediately recognize this shape of the A weighting curve as I showed to you on the slide a couple of minutes before. So this is the activated A weighting for pink noise, and I can do the same for C weighting, and you will recognize the corresponding shape as well with the damping here at the low frequencies and at the very high frequencies. By the way, these bars up here are the LC peak, so they are always higher than my live level. With my instrument, I can also show you the 12 octave resolution, which is even higher. Please keep in mind that you need this special option for this feature. Well, with pink noise, it's not very impressive, but you see we have a much higher resolution of our frequency spectrum. Good. Let me return to my presentation. And I want to show you some typical applications that you might encounter. I just start here with the German DIN standard for live events, which for instance requires 99 dB A weighted for the LAQ is the maximum level that is allowed. The sound level must not exceed an LC peak level of 135 dB. And this is another aspect that I presented to you. The measurement has to execute it in the synchronized repeated mode with a duration of 30 minutes. In contrast, if we look at the Swiss standard for the same application, live events, we have different levels, but I have selected here the 100 dB level. We have this as maximum limit. We have for the LAF max, in contrast to the LC peak in Switzerland, the LAF maximum is the limit for the highest level that may occur, 125 dB. And here we have a gliding recording over 1 hour instead of 30 minutes repeated synchronized. So here you can see that by reading these standards, you will find out the relevant parameters that have to be adjusted for your recording. And then I want to give you a completely different standard. This is the EU standard for the workplace noise. So here it says that the exposition level over 8 hours must not exceed 80 dB or 135 dB for the LC peak unless you are providing hearing protection to your workers. If you comply to this level here, then the employer is free to use a hearing protection. But if we exceed these levels, for instance, if the exposure level goes up to 85 dB or 137 CPK, then you must force your employees to use a hearing protection. And if the environmental noise is even higher, then these hearing protectors have even been optimized for the corresponding environment. Maybe you have asked yourself, what is LEX standing for? In this case, if you read the standard, you will see that this is the same as the LAEQ for 8 hours. So this is another example how you can familiarize yourself with the corresponding requirement by reading the standard and understanding the corresponding parameters. Well, my last slide refers to the data analysis and the reporting. We are providing free of charge Excel templates that can be downloaded from our website for the reporting. And we have a more sophisticated tool, the Data Explorer, which supports a number of post-processing and data analysis tools, as well, of course, the reporting. Let me very briefly show that to you. We have here the Excel sheet. We can change the color, the language in the Excel sheet. We can edit the entries, the manual entries for the name of the environment, for the environmental temperature, and whatever the person who was responsible. And the Excel sheet, by pressing this button, will automatically load the recording that we have saved on the PC. And on this tab, you see here the time history of the event. And the other example I want to show you is the Data Explorer. Please excuse, I have here the German version, but this is also available in English language, of course. So the Data Explorer offers a number of tools. It not only shows the time history of my event, it also shows you the spectrum over that time. We have here the audio file bar, so you can click on any position and it will replay the audio file at that time. And you have many more statistical tools included in this package. I don't want to explain it, would go too far, but just to let you know, if you want to do some post-processing of an environmental measurement, environmental noise measurement, then the Data Explorer is the perfect solution for you. Well, I'm at the end of this presentation. Just now, I would like to point out the subsidiaries that we have all over the world. So if you have any additional question now or in future, you may address us here in the headquarters or our subsidiaries or our independent partners that you will find in all the relevant countries worldwide. Thank you very much for today. Have a good time and see you soon. Bye-bye.